Hey class, today we're going to be doing section 4.2 in our college algebra course, which is logarithmic functions. I love logarithms. They're so much fun and very useful in real life, which is really cool. So the definition of a log function: for x greater than 0 and b greater than 0, b can't be 1. We have y equals the log base b of x. Now, this log function is equivalent to the exponential function b to the y equals x. So one of the things I want you to note is when I have y equals the log base b of x, this is the base, and it's going to remain the base when we switch it to exponential form. Now this ends up being the exponent. So what I always like to tell my students, and I write it in really big letters across my board in class, is the log is the exponent. So if you're wondering what is a log, what's a logarithm? The log is the exponent. So if I'm asking you to evaluate a log, I'm asking you to think, what's the exponent to the base? And I'll give you another, we'll do some examples together so you really understand, but just keep thinking, what is the exponent? The log is the exponent. So I'm looking for the exponent. So here, if my base is b, my exponent is y, we get this b to the y equals x. So these are the equivalent pieces of the same thing, just one's in log form and one's in exponential form. All right, so you can see that again here. Example 1, so let's practice changing from log to exponential form. So we have 2 equals log base 5 of x. So the base is 5, so we start with that. So exponential form, I'm looking for the base of something with an exponent, and I'm going to use m equals n. So something in that form. Base is 5, my exponent is 2, because the log equals the exponent, equals x, which we call the argument of the log. So if I wanted to solve this equation, x would be 25. Here we've got b, the base b is just b, to the third power is 64. And then I could solve that. What to the third is 64. Part C, we have 3 to the y power is 7. That would definitely be more of a decimal answer, a little harder to do in our heads. All right, so going the opposite direction, writing it in log form. So I'm looking for something like log base b of n equals m. So that's my goal, is to write it in this form. So I'm going to start by writing the letters log for log. The base of the exponent becomes the base of my log. So make sure you write the base smaller and lower than the line of everything else. Everything else should be in line. So the log, just kind of how you can see, let me get a different color here. So like if this was the line of my paper, all of those are in line with each other in the same size, and then the base is below that line and a little bit smaller. It's important that it looks like that when you write it. So log base 12 of x equals 2. Remember, the log is the exponent, so the exponent has to go on the other side of the equal sign. Log base b of 8 equals 3. Log base e, and now this one's going to be a little different. Log base e of 9 equals y. This is the same, I'm going to write same as the ln of 9 equals y. So if you notice on your calculator, we have a log button. So buttons on calculator. The log, just log, has a base of 10, because we use base 10 systems in the real world all the time, especially in science. And then ln, and I use a little cursive L so it doesn't look like a 1, this has a base of e, and we saw one example of an application of e in our last lesson, which was continuous compound interest. We also use it for population growth, things like that. So we use that a lot as well. So we have a special button in our calculator for that to make our lives a little easier. All right, so now let's talk about evaluating logs. So we've practiced writing it from one form to the other, and it's really important that you practice that a lot and really get comfortable with going in between forms. So without a calculator, what is the log base 2 of 16? So remember, I'm asking you, what is the exponent? That's what I'm asking you. So if my base is 2, what is my exponent so that I get 16? This is the question. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So we have 2 to the 4th power is 16. So the log base 2 of 16 is 4. So logs aren't as scary as they seem like they should be. If you're just thinking, okay, what's the exponent? I think it'll make a whole lot more sense. Log base 7 of 1 over 49. So I want 7 to the what power equals 1 over 49. Now notice 49 is 7 squared. So it's really like 7 to the what power is 1 over 7 squared. Well, we use negative exponents when we want things to become fractions. So that would be a negative 2 exponent. 25 to the what power is 5. So the log base 25 of 5 is what? Well, the square root of 25 is 5. And if you don't remember, the square root of x is the same as x to the 1/2 exponent. So fractional exponents are roots. Negative exponents make fractions. Fractional exponents make roots. All right, and then part D, I don't know what happened with my little square root and why there's 2 of them, so just ignore that. So 2 to the what power, the log base 2 of the 5th root of 2 equals blank. So 2 to the what power is the 5th root of 2. So again, I can rewrite the 5th root of 2 as 2 to the 1/5 power. So my answer here is going to be 1/5. All right, so hopefully you're feeling a little bit more comfortable with logarithms. You've got lots of practice in your homework. All right, basic log properties. So log base b of b. So if the base is the same, for example, if I have log base 5 of 5, what is that going to equal? Remember, what's the exponent? 5 to the what exponent is 5? It's 1. So the log base b of b, whenever that base and the argument match, you're going to end up with just 1. Log base b of 1, so remember b to the what power equals 1. Well, b to the 0 is 1. Anything to the 0 power is 1. Again, if you're not sure about some of these, because the last 3 and 4 get a little more complicated, write it in exponential form and see if you can figure it out. So if I write this in exponential form, I have b to the what power equals b to the x. Well, then that blank has to be an x. B to the x equals b to the x. All right, and then 4, so now this one's in exponential form. It's a base with an exponent equals something. I know the exponent has a log in it, but this is in exponential form. So in log form, it would look like this. Log base b of what equals the exponent? Log base b of x. So when we write it like that, and it was a little tricky to do that one, it's fairly simple to see that the blank has to be an x for the 2 sides of the equation to be equal to each other. All right, so on our next page, we're going to evaluate these without a calculator. So again, if you're struggling using those properties we just learned, change them to exponential form and then see where you go from there. So 7 to the what power is 7? And I would suggest pausing the video, seeing if you can do these 4 problems without me, and then checking your answer. So this is going to be 1. Log base 5 of 1 is 0 because 5 to the 0 power is 1. 4 to the what power is 4 to the 5th. That would be 5. And log base 6 of what equals the exponent, log base 6 of 36. This is going to be 36. All right, we're going to shift gears a little bit and do 2 graphing problems. So we talked about graphing exponential functions before, and now we're going to talk about graphing log functions. And what I want you guys to kind of realize, and because of the whole pandemic, we skipped inverse functions, but exponents and logarithms are inverses of each other. So if I graphed y equals 2 to the x, which we graphed in our previous lesson, this is the inverse to y equals log base 2 of x. So they both have the same base, but they're inverses, which means they would be reflections of each other. So reflections over the line y equals x, which is a diagonal line through our graph. I guess this way for you guys because I'm mirrored. So when we graph, if we think about what an exponential function looks like and we flip it, we reflect it across the line y equals x, we'd get a log function. So kind of keep that in mind. All right, so what I would suggest you do first is change to exponential form. So if I have y equals log base 2 of x, I'm going to change this to exponential form. I get 2 to the y equals x. Remember, the log is the exponent, so y becomes the exponent. When I make a table of values, it's going to be a little weird. This is the first time where it's actually easier if we input values for y instead of x. So I'm going to do -2, -1, 0, 1, and 2 for y. Plug those in and get the x values. So 2 to the -2 power is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2, and 2 squared is 4. Now, when I graph these points, be really careful. Don't mix them back up. So x is 1/4, y is -2. So if I go 1/4, -2, I get something like this. -1. Okay. 1/2, -1. 1, 0. 2, 1. And 1, 2, 3, 4. 1, 2. So now, if we got more negative in the y direction, the fraction would get smaller and smaller and smaller, closer to 0 in the x direction. So this is really feeling similar, but flipped. It's like what we saw with exponential functions, but instead of the y getting closer to 0, it's the x getting closer to 0, which means instead of a horizontal asymptote, we have, drum roll please, a vertical asymptote. Now, when we talked about horizontal asymptotes, we talked about the purpose of a horizontal asymptote was to denote the end behaviors of a graph. Vertical asymptotes are different. So vertical asymptotes represent some part of the function where it's like undefined. So you really, really can never touch a vertical asymptote. In the future, it's actually okay to touch a horizontal asymptote in the middle of your graph somewhere, but it's never okay to touch a vertical asymptote. So when you draw your graph, be really careful. If you touch that vertical asymptote, I'm taking off points. Okay. So now let's look at, so here's our log function. That's what a log graph looks like. Domain, and now domain is not all real numbers. Look at the x direction. How far left and how far right is this function going to go? Well, it's going to go x values greater than 0, or from 0 to infinity if you're using interval notation. Notice I didn't say or equal to. Because of that vertical asymptote, it's never going to actually equal 0. My range happens to be all real numbers, or -infinity to infinity. My asymptote, I have a vertical asymptote at x equals 0. And my end behavior is going to be a little weird, so bear with me here. As x approaches infinity, in this case, because x is going to the right, we can go to the right towards infinity. F of x approaches infinity. Slowly but surely, it'll get all the way up there. Now, the left end of the graph. How far left does it go? Does it go to negative-infinity? No, it doesn't. So I can't say as x approaches negative-infinity. I need to say as x approaches, where is it approaching? What is the graph approaching in the x direction? In this case, it's approaching 0. That's our vertical asymptote. Then f of x, as that happens, as I get closer and closer and closer to 0, this graph keeps going down forever to negative-infinity. So the end behavior for logs is a little different. All right, let's do one graph with a transformation as our last example for today. So now when you graph with transformations, what I would suggest you do is write out or kind of describe your transformations first. So here I have a movement 3 to the left, and I'm going to do a star on my graph where that movement is. So we kind of did a similar thing like this with our exponential functions. So 3 to the left, I'm going to put a star on my graph from my origin 3 to the left. Now I'm going to take the plus 3 out of my equation. So I'm going to rewrite the equation y equals log base 4 of x without the transformations. Change it to exponential form, 4 to the y equals x. Make an xy table with this. It's going to be easier to manage. -2, -1, 0, 1, and 2 for the y values, because those are my exponents. 4 to the -2 is 1/16. 4 to the -1 is 1/4. 4 to the 0 is 1. 4, and 16. Now these aren't coordinate points because these are a table made from just log base 4 of x. I don't have log base 4 of x. I have log base 4 of x plus 3. So it's all these points moved 3 to the left. So what I like to think of these is over and up from my shifted point at -3, 0. So from -3, 0, if I go over 1/16, I'm going to go down 2. If I go over a quarter, I'm going to go down 1. Over 1, down 0. So I'm basing everything from my starred point on my graph. If I go over 4, 1, 2, 3, 4 to the right from the star, I'm going to go up 1. If I go over 16, it's not going to fit on my graph. So I can just stick with what I have here. And what I would strongly suggest is learn that logs have vertical exponents and draw the vertical asymptotes. Draw the vertical asymptote first before you draw your curve. That will remind you that when you're drawing this curve, you cannot go and touch that value there. And then be careful as you go more positive not to cross the next y value, because it doesn't actually cross that next y value until we get to 16 over from our star, which we don't see on our graph. So be careful. All right, so my domain in this case, so this was -3. I should always at least number one number on each axis so I know what I was counting by. My domain is going to be from -3 to infinity, or x greater than -3. My range is still all real numbers, -infinity to infinity. My vertical asymptote is at x equals -3. And my end behavior, as x approaches infinity, f of x approaches infinity, slowly but surely. And as x approaches -3, because that's as far left as it's going. When we talk end behavior, we're not talking infinities. We're talking the right and the left ends of our graph. So where are they going? As x approaches -3, f of x goes down to -infinity. All right, and there is a log function graph with a transformation. And that's it for today's lesson.